Bismillahirrahmanirrahim. Assalamu alaikum. It's our lecture 5 today, and our topic is Fast Fourier Transform. What is Fast Fourier Transform? An algorithm that computes the discrete Fourier transform of a sequence or its inverse discrete Fourier transform. Frequency analysis converts a signal from its original domain, often time or space, to a representation in frequency domain, and vice versa. Okay, what we have to do in fast Fourier transform, we have to find the discrete Fourier transform or its inverse, like we did in our last lecture. And what is Fourier analysis? In Fourier analysis, we actually convert our signal, whether it is in time or space domain, to its frequency domain representation. In our first or second lecture, we also studied about the unsorted and sorted data and their corresponding search types. Uh, if we have unsorted data or some random data, we apply linear search on it, and the big O, which is the worst case, is big O into n, which shows that we have to do n number of iterations to find our desired value. But in case of sorted data, binary search, our big O is log of n base 2, which tells if capital N is equals to 10, then we would have to do 4 iterations to get our required value. This is the formula for the DFT, the discrete Fourier transform. In this case, the additions we have to do is equals to n into n minus 1, and the multiplications is equals to n square, where small n is from 0 to n minus 1, same for the k. Multiplying is more intense as compared to the addition. In DSP works on a rule which is divide and conquer. For example, if we have a large problem, we'll convert it into small problems, then get a solution of those small problems, and our big problem will also be solved. We have an example. We have a signal with 8 values in it, and we'll check. First of all, we'll apply our discrete Fourier transform on it. And do you know anything, the most important thing about a system or a Fourier transform is that what is its computational cost. In every discipline, we have to apply such algos on it that it give us that it take very small computational cost. For example, here this is our signal, and after applying this formula of discrete Fourier transform, we get these 8 values. In this case, the addition and the number of additions and multiplications are 56 and 64. Now we'll try to reduce our computational cost. How we'll do that? We will try to do that by separating our signal into even and odd values. Let wn is equals to e raised to power minus j 2 pi n. We have just replaced this factor e raised to power minus 2 pi j over n, except nk. We have suppose this factor equals to wn, and on putting the value of this, which is equals to wn, in this we get this formula. For example, if kn is equals to capital N, then by solving this e raised to power minus 2 pi is equals to 1, and if small n is equals to 1, then we will get here will only a k value, and we'll get e raised to power minus j 2 pi k, and the value of this factor depends upon k. Same for this. Now to solve this, we'll divide it into even and odd indexes. We have just rewrite this formula two times, one for the even and one for the odd. And for the even part, let n is equals to 2r, and for the odd part, let n is equals to 2r plus 1. On solving these, if something is adding in the power, it means that their bases are same and their indexes are multiplying. So we can separate these two terms from this, and then after solving we'll get this. This is the even part and this is the odd part, and odd part is multiplying with the w or omega n k, and let even part is equals to a and odd part is equals to b. So in the first case we didn't divide our signal into even or odd, but in the second case, let's check 4-point DFT, in which we have divided our signal into even and odd part. On solving even 4-point DFT, this is the formula, and on solving the even part, this even part where x of 0 is equals to -4, 1, 0 and 1, 2, 3, -2 and 3, or after applying the DFT on it, we get these answers, which are just 6, 4, -6, 4. And in case of odd part, on applying the discrete Fourier transform, we get these answers, which are -2, 4, -6, 4. So as we have derived this formula, in this formula this is the even part and this is the odd part multiplying with this factor. So we'll do the same thing here. This is the even part and this is the odd part. We'll multiply this odd part with this factor as w04, where okay, and on solving we'll get the same values as we get in the first case here, without dividing our indexes into even and odd parts. So on dividing our signal into even and odd parts, our addition and multiplication were reduced to 82 to 32 and 40. How? The formula for the addition was n into n minus 1, and we have divided our signal into 4 even and 4 odd parts. So n is equals to 4 into 3, then we get 12, and 12 into 2, as we have divided into 2 parts, so multiply by 12, and a total number of samples were 8, so we get 32. And in case of multiplication we got 40. In the first case, there were 56 number of additions and 64. We have reduced our number of addition and multiplications to 32 and 40. Now in case of 2-point DFT, we have divided our signal into 2-point DFTs, and we got four separate boxes, and on solving we again get the same result. And now in this case our multiplication has reduced to 24 and addition to 16. And at the end of our lecture we will also go through from the decomposition with respect to time. What is actually the decomposition with respect to time? It is the short time Fourier transform. It is actually the short time Fourier transform, which is a Fourier related transform used to determine the sinusoidal frequency and phase contents of local section of signal as it changes over time. from this example we can better understand this. For example, we have a signal from 0 to 4. There was some man talking, and from 4 to 8 here is some music, and from 8 to 10 again a voice note. So this signal was in the time domain. On doing the frequency analysis or the Fourier analysis, we actually convert this signal into the time domain in separate and separated them. From 0 to 4 we'll get a low frequency. The maximum frequency here will be some lowest, some would have some less amplitude. And in the second part from 4 to 8, as it is the result of some music, so here our signal will be from 0 to 32 kilohertz. Its frequency will be 32 kilohertz, and from 8 to 10 it's again will be 8 kilohertz. So our signal was in time domain. We converted into frequency domain separately, and if we combine these three signals, we'll again get 32 kilohertz, which shows that in this signal we do not know how many signals are there in it, how many different signals are there in it, but on changing it into time domain, we know that here are three signals of frequency of 8 kilohertz, 32 kilohertz, another with 8 kilohertz. So that's all for today. Thank you so much.